Okay. In the first section, we're talking about chemical names and formulas. We want to understand the significance of chemical formulas. We want to determine the formula of an ionic compound formed between two given ions. Name an ionic compound given its formula. Use prefixes, name a binary molecular compound from its formula. Write the formula of a binary molecular compound given its name. So what is a chemical formula? Why is it important? When we look at chemical formulas, they tell us things. Okay, this is the language of chemistry, and it's going to tell us the relative number of atoms of each kind in the compound that we're dealing with. So when we look at a molecular compound, remember molecular compounds are going to be those that are covalent. Molecular compound, the chemical formula reveals the number of atoms of each element contained in one molecule of the compound. That's important. It's representing for us one molecule of that thing and the numbers of atoms within that one molecule. So you've got octane, which is C8H18. Okay, this is one molecule. And the subscript after the C indicates that there are 8 carbon atoms in this one molecule. And the subscript after the H tells us that there are 18 hydrogen atoms in this molecule. And it's one molecule. When we talk about the chemical formula for an ionic compound, what that does, okay, this is different now. We're talking about ionic compounds. It represents one formula unit, and a formula unit is the simplest ratio of the positive ions, the cations, and the negative ions, or the anions. An example of this would be aluminum sulfate, which is Al2SO43. When you see the parentheses are going to be around what we call a polyatomic ion. So SO4 is actually an ion with a -2 charge. And the parentheses within the formula help us identify it as one unit. So it comes together. The SO4 comes as one thing, and the SO4 bonds to the Al2s. Okay? And the subscript in particular on the other side of the parentheses there, that 3, represents the unit. We can note when we look at these chemical formulas for ionic compounds that there is no subscript for the sulfur. When there is no subscript next to an atom, the subscript is understood to be 1. So, and typically in math, in these chemical formulas, we don't write the 1. Okay, if there's no subscript there, then it means there's one of those things, or whatever that thing is. When we talk about monatomic ions, this is where we have main group elements that are able to lose or gain electrons to form ions. And ions formed from a single atom are known as monatomic. That should make sense to us. Atomic, mon meaning one. These are monatomic ions. So to gain a noble gas electron configuration, nitrogen gains 3 electrons to form N3 minus ions. That would be the charge on the nitrogen is a -3. It's gained 3 electrons. And then we have main group elements that form covalent bonds instead of forming ions. So carbon and silicon are going to be more apt to form covalent bonds than to actually form ions. So how do we name monatomic ions? There's actually rules for this, and you're going to need to at least start to comprehend these rules and apply them to questions. The cations are identified simply by the element's name. So, the potassium ion is basically called potassium cation. Magnesium, magnesium cation. When we have anions that are monatomic, this is the negative ion, right? The ending of the element's name is dropped, and the ending IDE, ide, is added to the root name. So there's fluorine, okay? We'll take out the ene and add the IDE, and this is now a fluoride anion. The nitrogen that we talked about, well, it would be called a nitride anion. This is a rule you're going to have to remember and be able to apply. And this chart gives you common monatomic ions, whether they have plus 1, 2, or 3 charges or negative 1, 2, or 3 charges, and what their names would be. And then these would be the D block elements that form monatomic ions. All right, we can talk about binary ionic compounds. These are compounds where two elements come together and it's known as binary. In binary ionic compounds, total numbers of positive charges and negative charges must be equal. So that's one of the things you got to look for if you're doing problems with these. The negative and positive charges have to be able to cancel each other out. The formula for a binary ionic compound can actually be written given the identities of the compound's ions. It can be written because you have to know that the positive and negative charges have to be able to cancel each other out. So an example would be magnesium bromide. From that name, based on what we've already learned, okay, you know what your ions are going to be. So it's going to be a magnesium, right? And it's going to be a bromine. If you know that magnesium is going to form +2, then you know that you're going to need 2 bromines to cancel out that charge. And your chemical formula is going to be MgBr2. So a general rule in trying to do this when you're determining the formula from a binary ionic compound is crossing over to balance charges between ions. What do we mean by that? Well, let's look at aluminum oxide. Write the symbols for the ions. There's Al3+, and then there's O2-. Cross over the charges by using the absolute value. So that would be Al3+2, but then your O2 negative is going to be a 3. Each ion's charge has a subscript for the other ion. You can see that there better than I can explain it and understand why it's called crossing over. When you do that and you have this, you check the combined positive and negative charges to see if they're equal. Well, if you have 2 aluminums and they each have a +3 charge, that's +6. If you have 3 oxygens and they each have a -2 charge, that's -6. So they're equal. They cancel. So that's your correct formula for aluminum oxide, Al2O3. And there's a whole bunch of rules here. I'm not going to read them, but you should learn them and you should memorize them. These are the rules for writing the formula of ionic compounds. This is on the slide, but it's also available in your textbook. Now, naming binary ionic compounds. How do we come up with the names, or what we call the nomenclature, the naming system? Binary ionic compounds involves combining the names of the compound's positive and negative ions. So you have the cation, you give the name of the cation as first, followed by the name of the anion. So, Al2O3, we just did. Well, the name of the cation is just the name of the element, aluminum, and then the name of the anion is where you add the IDE, and so this would become aluminum oxide. Simple ionic compounds, the ratio of the ions is not given in the compound's name because it is understood based on the relative charges of the compounds. So we don't give ratios in the name, we just call it what it is because the formula shows us the ratio is pretty simple. So write the formulas. In terms of a sample problem, how does this work? Write the formulas for the binary ionic compounds formed between the following elements. So you got zinc and iodine, zinc and sulfur. First we write the symbols for the ions side by side. You always write the cation first. And obviously if you don't have these memorized, you look them up in the chart. Cross over the charges to give the subscripts. Check the subscripts, divide them by their largest common factor to give the smallest possible whole number ratio of ions. Largest common factor is 1 in this case. Smallest possible whole number ratio of ions in the compound is 1 to 2. And remember, you've got to do this step because you always need to give these formulas in the smallest possible whole number ratio. So for the first one would be ZnI2. See the second one? In this case, the largest common factor of the subscripts is 2. So the smallest whole number ratio is 1 to 1. And this would be ZnS. Now, the stock system of nomenclature. You have elements like iron, which form 2 or more cations with different charges. To distinguish the ions formed by such elements, scientists use what we call the stock system of nomenclature. And this is where you've seen these formulas with Roman numerals to indicate the ion's charge. So, Fe2 plus would be iron, Roman numeral 2. Fe3 plus would be iron, Roman numeral 3. We do this because there are these certain elements that form more than one ion. So placing that into a sample problem, write the formula and give the name for the compound formed by the ions Cr plus 3 and F minus. First we write the symbols side by side. Make sure you always write the cation first. Cross over the charges to get the subscripts. That would look like that. That's how we work out the charges. Largest common factor of the subscripts is 1, so the smallest whole number ratio of the ions is 1 to 3. The formula is CrF3. But we know that chromium forms more than one ion, so the name of the 3 plus chromium ion must be followed by a Roman numeral indicating its charge. So the name would not be chromium fluoride, but rather chromium 3 fluoride. And then we have these polyatomic ions that are fairly common called oxyanions. These are polyatomic ions that contain oxygen. And what we have is elements that can combine with oxygen to form more than one type of oxyanion. So nitrogen can form NO3 negative or it can form NO2 negative. The name of the ion with the greater number of oxygen atoms ends in ATE. The name of the ion with the smaller number of oxygen atoms ends in ITE. Notice, guys, one of the things you're getting here, once again, are rules that need to be memorized in order to do these problems correctly. So the NO3 is nitrate, the NO2 is nitrite. And then we've got elements that can form more than 2 types of oxyanions. Chlorine, you've got, ClO, ClO negative 2, ClO negative 3, ClO negative 4. What we do in this case, we have the anion that has 1 fewer oxygen atom than the ite anion is given the prefix hypo. The anion that has 1 more oxygen atom than the ate anion is given the prefix per. So the ClO negative would be hypochlorite. ClO2 would be chlorite. ClO3 would be chlorate. ClO4 would be perchlorate. And then here's a list of the polyatomic ions with their charge and their names and what their formulas are. And again, a list of rules for naming compounds with polyatomic ions. I'm not going to read all these, but you need to familiarize yourself with them. This just helps us understand the formulas for polyatomic ionic compounds. K2SO4, you've got the sulfate ion, which is SO4 -2. You've got the potassium ions, which is the positive K, right? Two of those attached to one SO4. KNO3 is a nitrate ion bonded to a potassium ion. Notice it's not a potassium and a nitrogen bonded together and then 3 oxygens bonded to that. So the idea here is that you can't move atoms from one polyatomic ion to the next. Elements of polyatomic ions are bound together in a group and carry the charge. So it's these groups, it's these polyatomic ions that are a group of things bonded together. They always have to stay together. So compounds containing polyatomic ions. Another sample problem, write the formula for tin 4 sulfate. Cross over the charges to give subscripts. Add parentheses around the polyatomic ion if necessary. So this would be SN4 plus and then SO4 -2. Cross over the charges. There's your cross charges. There's your parentheses. Total positive charge is +8. Total negative charge is -8. Largest common factor of the subscript is 2, so the smallest whole number ratio is 1 to 2. The correct formula ends up being SN, then SO4 The SO4 is in parentheses. The 2 is outside of the parentheses, meaning that there are 2 SO4 polyatomic ions that are bonded to the tin. Naming binary molecular compounds. So now we're moving on. This is not ionic compounds. These are molecular compounds. These are things composed of individually covalently bonded units or molecules. These are the covalents that we learned about in Chapter 6. As with ionic compounds, there is a stock system for naming molecular compounds. The old system of naming molecular compounds is based on the use of prefixes. So CCl4 would be carbon tetrachloride, tetra equals 4. CO would be carbon monoxide, mon equals 1. CO2 would be carbon dioxide, di equals 2. You get that. There are your prefixes with examples. Again, things that you need to memorize. So, give the name of AS2O5, write the formula for oxygen difluoride. 2 different problems. You need to be able to work naming in both directions. Chemical formulas and names, you need to be able to work in both directions. So, a molecule of the compound contains 2 arsenic atoms. The first word in the name is diarsenic. The 5 oxygen atoms are indicated by adding the prefix pent to the word oxide, right? Pent means 5. So the complete name is diarsenic pentoxide. Next, we have oxygen is first in the name because it is less electronegative than fluorine. Because there's no prefix, there must be only 1 oxygen atom. The prefix di in difluoride shows that there are 2 fluorine atoms in the molecule. The formula is OF2. We've got covalent network compounds. Some covalent compounds do not consist of individual molecules. So instead, each atom is joined to all its neighbors in a covalently bonded 3-dimensional network. Subscripts in a formula for covalent network compound indicate smallest whole number ratios of the atoms in the compound. Examples would be SiC, which is silicon carbide, SiO2, silicon dioxide, Si3 and 4, trisilicon tetranitride. Then we have acids and salts. Acid is a certain type of molecular compound. Most acids used in the laboratory are either binary acids or oxyacids. Binary acids consist of 2 elements. A lot of times it's hydrogen and a halogen. Oxyacids are acids that contain hydrogen, oxygen, and a third element, usually a nonmetal. When you're in the laboratory, in chemistry we use the term acid. It's going to refer to a solution in water of an acid compound rather than the acid itself. Hydrochloric acid refers to a water solution of the molecular compound hydrogen chloride. Polyatomic ions are produced by the loss of hydrogen ions from oxyacids. So, sulfuric acid is H2SO4, sulfate is the polyatomic ion. Nitric acid is HNO3, nitrate is the polyatomic ion. Phosphoric acid is H3PO4, phosphate is the polyatomic ion. Ionic compounds composed of a cation in the anion form an acid is often referred to as a salt. So, table salt NaCl contains the anion from hydrochloric acid HCl. Calcium sulfate CaSO4 is a salt containing the anion from sulfuric acid H2SO4. Bicarbonate ion HCO3 comes from carbonic acid H2CO3, and this is why when you take an acid and mix it with a base, one of the products you get is a salt. Alright, so now we're going to look at part 2 of this chapter, and this deals with oxidation numbers. And what we want to be able to do is understand, know, and list the rules for assigning oxidation numbers, be able to give the oxidation number for each element in the formula of a chemical compound, name binary molecular compounds using oxidation numbers and the stock system. So obviously, guys, this is building on the first section. What are oxidation numbers? The charges on the ions in an ionic compound reflect the electron distribution of the compound. Hopefully we understand that by this point. If something has a +3 charge, it means that it lost 3 electrons. It now has 3 more protons than it does electrons. And in order to indicate the general distribution of electrons among the bonded atoms in a molecular compound or a polyatomic ion, oxidation numbers are assigned to the atoms composing the compound or the ion. So these are a little different. Unlike ionic charges, oxidation numbers do not have an exact physical meaning. Rather, they serve as a useful bookkeeping tool to help keep track of electrons. So remember this, guys. The oxidation numbers are not necessarily or absolutely the same thing as telling you specifically what the charge is, how many electrons are there, how many electrons have been lost, how many electrons have been gained. So how do we assign oxidation numbers? In general, when assigning oxidation numbers, shared electrons are assumed to belong to the more electronegative atom in the bond. So remember, right, you're going to have 2 atoms bonded together. One's going to be more electronegative than the other. The one that's more electronegative, we're basically going to think of the electrons as belonging to that one. And then there's more specific rules. Atoms in a pure element have an oxidation number of 0, so you keep that in mind. So if you get an atom on a pure elemental form, its oxidation number is 0. So atoms in sodium or oxygen or phosphorus, sulfur, they all have oxidation numbers of 0 because all you have is sodium. So all the atoms, oxidation number, that's pure elemental form. O2 is oxygen. It's oxygen in its elemental form. So the oxidation numbers are going to be 0. Next, the more electronegative element in a binary compound is assigned a negative number equal to the charge it would have as an anion. Likewise for the less electronegative element. Fluorine has an oxidation number of -1 in all of its compounds because it is the most electronegative element. Oxygen usually has an oxidation number of -2. There are exceptions. Peroxides like H2O2, which is hydrogen peroxide, oxidation number of oxygen is -1. Compounds with fluorine, OF2, the oxidation number of oxygen is +2. Hydrogen has an oxidation number of +1 in all compounds containing elements that are more electronegative than it. It has an oxidation number of -1 with metals. The algebraic sum of the oxidation numbers of all atoms in a neutral compound is equal to 0. The algebraic sum of the oxidation numbers of all atoms in a polyatomic ion is equal to the charge of the ion. Although rules 1 through 7 apply to covalently bonded atoms, oxidation numbers can also be applied to atoms in ionic compounds similarly. So, how does this all, those are the rules. Again, guys, another list to memorize. How does this all work out? Assign oxidation numbers to each atom in the following compounds or ions. So you've got UF6, H2SO4, ClO3, polyatomic ion. So place known oxidation numbers above the appropriate elements. Multiply the known oxidation number by the appropriate number of atoms and place the totals underneath the corresponding elements. By the way, we know that fluorine is -1 because that was one of the rules. So we multiply -1 times the 6, and you end up with a -6 under fluorine. The compound UF6 is molecular. The sum of the oxidation numbers must equal 0. Therefore, the total of positive oxidation numbers is +6. Divide the total calculated oxidation number by the appropriate number of atoms. There is only one uranium atom in the molecule, so it must have an oxidation number of +6. All right, hydrogen has an oxidation number of +1. We know that because we learned it. Oxygen has an oxidation number of -2. We know that because we learned it. The sum of the oxidation numbers must equal 0, and there is only one sulfur atom in each molecule of H2SO4. Because +2 plus -8 is -6, the oxidation number of each sulfur atom must be +6. The total of the oxidation numbers should equal the overall charge of the anion, -1. So, this is for C. The oxidation number of a single oxygen atom in the ion is -2. Total oxidation number due to 3 oxygen atoms is -6. For the chlorate ion to have a -1 charge, chlorine must be assigned an oxidation number of +5. There you go. So how do we use oxidation numbers for formulas and names? You'll see the table in the next slide. You have lots of nonmetals, can have more than one oxidation number. These numbers can sometimes be used in the same manner as ionic charges, helps us determine formulas. So if we were to ask what is the formula of a binary compound formed between sulfur and an oxygen, from the common +4 and +6 oxidation states of sulfur, you could predict that sulfur might form SO2 or SO3. And both are actual compounds of sulfur and oxygen that do exist. So here's the table. Common oxidation states, group 14, carbon. Can be -4, can be +2, can be +4. Look at group 15, nitrogen, whole bunch there, phosphorus, sulfur, again. So in addition to the values shown, atoms of each element in its pure state are assigned an oxidation number of 0, which you knew because that was part of the rules. So if we use oxidation numbers and the stock system, which we've already introduced, you can use as an alternative to prefix system for naming binary molecular compounds. So the prefix system says that PCl3 would be phosphorus trichloride, PCl5 would be phosphorus pentachloride, N2O would be dinitrogen monoxide, NO would be nitrogen monoxide, MO2O3 would be dimolybdenum trioxide. But if we use the oxidation states and the stock system, PCl3 becomes phosphorus 3 chloride, PCl5 becomes phosphorus 5 chloride, N2O becomes nitrogen 1 oxide, NO becomes nitrogen 2 oxide, MO2O3 becomes molybdenum 3 oxide. Alright, so now in section 3 of this chapter, guys, we're going to look at, in more detail, how we actually can use chemical formulas to figure out things, right? So we can, and some of this may be in some sense some kind of review, we can calculate the formula mass, molar mass of any compound. We can use the molar mass to convert between mass in grams and amount in moles of a chemical compound. We can calculate the number of molecules, formula units, or ions in a given molar amount of a chemical compound. Calculate the percentage composition of a given chemical compound. So what does a chemical formula tell us? It tells us the elements present in that particular compound. It tells us the relative number of atoms or ions of each element present in that compound. And chemical formulas allow chemists to calculate a number of other characteristics and values for the particular compound that they're looking at. We can figure out formula mass, and we can figure out molar mass, and we can figure out percentage composition. Slightly different applications from what we learned, but very similar to some of the math we've already done in this class, guys. So what's formula mass? The formula mass of any molecule, formula unit, or ion is the sum of the average atomic masses of all atoms present in its formula. So let's look at that in terms of the formula mass of water, which is H2O. The average atomic mass of hydrogen is 1.01 AMU. The average atomic mass of oxygen is 16.00 AMU. So we've got 2 hydrogen atoms times 1.01 AMU over a hydrogen atom. Cancels out hydrogen atoms, gives us 2.02 AMU for hydrogen. 1 oxygen atom over or times 16.00 AMU over oxygen. Cancel out oxygen atom, gives us 16 AMU, and we know that the average mass of a molecule of H2O is 18.02 AMU. Pretty simple, nothing new here. The mass of a water molecule can be referred to as its molecular mass. That's the mass of one molecule of water. The mass of one formula unit of ionic compound, such as NaCl, is not a molecular mass. Remember, the mass of any unit represented by a chemical formula, H2O, NaCl, can be referred to as the formula mass. But with ionic compounds, those formulas tell us something different. So, look here. Formula mass of potassium chlorate, KClO3, is found by adding the masses of 1 potassium atom, 1 chlorine atom, and 3 oxygen atoms. Atomic masses can be found in the periodic table in the back of your book. In your calculations, round each atomic mass to 2 decimal places. So there is the atomic mass unit for potassium, atomic mass unit for chlorine, and atomic mass unit for 3 oxygens. So the formula mass of KClO3 is 122.55 AMU. In terms of molar mass of a substance is equal to the mass in grams of 1 mole, or approximately 6.022 times 10 to the 23 particles of the substance. So the molar mass of pure calcium, Ca, is 40.08 grams per mole, because 1 mole of calcium atoms has a mass of 40.08 grams. Remember, this is stuff we've already done. The molar mass of a compound is calculated by adding the masses of the elements present in a mole of the molecules or formula units that make up the compound. So 1 mole of water molecules contains exactly 2 moles of hydrogen atoms and 1 mole of oxygen atoms. The molar mass of water is calculated as follows. 2 moles of hydrogen times 1.02 0.01 grams of hydrogen over a mole of hydrogen equals 2.02 grams of hydrogen. 1 mole of oxygen times 16.00 grams of oxygen over a mole of oxygen equals 16.00 grams of oxygen. So the molar mass of H2O molecule is 18.02 grams per mole. Again, we figured this out. We know this. This is not new for us, guys. A compound's molar mass is numerically equal to its formula mass. If you figure out the formula mass, you know the molar mass. You just got to have the right unit, and it's a derived unit. It's grams per mole. This chart shows some of these just as another example. So what's the molar mass of barium nitrate? BaNO3 2. 1 mole of barium nitrate contains 1 mole of barium, 2 moles of nitrogen, 1 times 2, and 6 moles of oxygen, 3 times 2. Figure out for barium. Figure out for nitrogen. Figure out for oxygen. Molar mass of barium nitrate is 261.35 grams per mole. Now, as we've talked earlier, we can use molar mass as a conversion factor. The molar mass of a compound can be used as a conversion factor to relate an amount in moles to a mass in grams for a given substance. Again, this is math we've done. To convert moles to grams, multiply the amount in moles by their molar mass. So amount in moles times molar mass, grams per mole, equals mass in grams. Here are your conversion factors. We've seen this. We saw this in terms of the triangle. How to go from mass to amount. How to go from mass of element to number of atoms using Avogadro's number. These are your mole mass calculations. So, what is the mass in grams of 2.50 moles of oxygen? You know you have 2.50 moles of O2. You want to find the mass in grams. The moles of O2 equals grams of O2. So amount of O2 in moles times the molar mass, which is grams per mole, equal the mass. So you have 2 moles of oxygen times 16.00 grams of oxygen over a mole of oxygen equals 32 grams. Use the molar mass of oxygen to convert moles to mass. So you have 2.50 moles of O2 times 32 grams of O2 over moles. You're going to cancel out the moles. Your answer is going to be 80 grams of oxygen. Now, how do we convert between amount in moles and number of particles? Decide which quantity you are given, or number of particles. You're either given moles or number of particles. If you are converting from amount to number of particles, you go left to right. Use the top conversion factor. If you are converting from number of particles to amount, going right to left, use the bottom conversion factor in this chart that they give here. This should be all review, guys. Ibuprofen, C13H18O2, is the active ingredient in many non-prescription pain relievers. Its molar mass is 206.31 grams per mole. If the tablets in a bottle contain a total of 33 grams of ibuprofen, how many moles of ibuprofen are in the bottle? How many molecules of ibuprofen are in the bottle? What is the total mass in grams of carbon in 33 grams of ibuprofen? So this seems like a really big, complicated question, guys, but the principles are no different than what we were doing 3 or 4 weeks ago. You just need to make sure you break the problem down into its constituent parts. So you're given 33 grams of this. You're given the molar mass. You want to figure out how many moles, which means you got to set up your problem to get rid of grams. You want to figure out how many molecules, we'll talk about that, and total mass of carbon. So for A, you're going from grams to moles. Put grams of your molecule times 1 mole over the molar mass, grams, and that's going to give you your moles. In B, you want to go from moles to molecules, right? So you start with your moles. You're going to multiply by the conversion factor for molecules, which is 6.022 times 10 to the 23. That's Avogadro's number. It's always the number of things in a mole. Right now you're talking about mole of molecules, so, but the number stays the same. And you do that, and it's going to give you a number of molecules. And then you want to, in C, figure out the grams of carbon. Start with your moles, figure out moles of carbon, and then your grams. So that would be moles of your ibuprofen times 13 moles of carbon over moles of the whole product times 12.01 grams of carbon over the moles of carbon gives you the grams of carbon. So in the first one, we do 33 grams of C13H18O2 times 1 mole over 206.31 grams. And you do your canceling, and you get your 0.16 moles of C13H18O2. In part B, you started with your 0.16 moles times, so that's what you found in A. Now times 6.022 times 10 to 23 molecules over a mole. You're going to cancel out your moles, and you see that you have 9.6 times 10 to the 22 molecules of C13H18O2. In part C, you're going to start again with your moles of ibuprofen, okay? And you know that you have 13 moles of carbon because everything is, there's 13 atoms over the mole of the whole product times 12.01 grams of carbon over a mole of carbon. And you cancel out moles of C13H18O2. You cancel out moles of carbon. The only thing you have left is grams of carbon. That bottle is going to contain 25 grams of carbon. You can also do percentage composition. It's often useful to know the percentage by mass of a particular element in a chemical compound. To find the mass percentage of an element in a compound, the following equation can be used. Mass of element in the sample of compound divided by mass of sample compound times 100 gives you percent element in compound. The mass percentage of an element in a compound is the same regardless of the sample size, because you're figuring out percentage, the percentage, mass percentage. So it doesn't matter if you got 100 or if you got 500, the percentage should always be the same. The percentage of an element in a compound can be calculated by determining how many grams of the element are present in 1 mole of the compound. So mass of element in 1 mole of compound divided by molar mass of compound times 100 gives you percent of element in the compound. Then the percentage of by mass of each element in a compound is known as the percentage composition of the compound. Again, we've done these kinds of problems. So in iron 3 oxide, Fe2O3, iron is always 69.9%, oxygen is always 30.1%, no matter how much of the iron oxide you have. In iron 2 oxide, FeO, iron is always 77.7%, and oxygen is always 22.3%. Always, no matter how much iron 2 oxide you have. If you need to, memorize this. Here's your conversions, right? Percentage composition by mass. You work this, it'll get you in the direction you want to go. What does the sample problem look like? Find the percentage composition of copper 1 sulfide. This is Cu2S. How do we start? You've got your formula. You want to find percentage composition. You go from formula to molar mass to mass percentage of each element. What does that look like? Well, first 2 moles of copper, you get 127.1 grams of copper. 1 mole of sulfur, you get 32.07 grams of sulfur. Your molar mass, when you put everything together, molar mass of the whole formula, okay, the whole compound is 159.2 grams. Copper was 127.1 grams out of the 159.2 grams, means that copper is 79.85%. Sulfur is 32.07 grams out of the 159.2 grams, means that the sulfur is 20.15%. All right, guys, we're going to finish up Chapter 7 here, looking at Section 4, determining chemical formulas. This is really going to work backwards from what we learned in the last section. So we want to know what empirical formulas are and explain how they work with ionic and molecular compounds and what they tell us. Determine empirical formulas from the percentage or the mass composition. Explain the relationship between the empirical formula and the molecular formula of a given compound. And determine the molecular formula from an empirical formula. This chart just kind of gives you an idea, showing you a little bit of the empirical and actual formulas in terms of diagrams. So when an empirical formula, it's made up of, guys, it's made up of the symbols for the elements that are in the compound and subscripts that show the smallest whole number mole ratio of the different atoms in the compound. Notice the smallest whole number mole ratio, not necessarily the exact number of atoms. When you talk about empirical formula in terms of ionic compound, the formula unit is usually the compound's empirical formula. But when we talk about molecular compounds, the empirical formula does not necessarily indicate the actual numbers of atoms present. So for an example, the empirical formula of the gas diborane is BH3, but its molecular formula, which shows us the actual number of atoms bonded together, is B2H6. So to calculate empirical formulas, basically, you've got a process here where you determine the compound's empirical formula from the percentage composition. You start by converting percentage composition to mass composition. You do that by assuming you have a 100-gram sample. That's real easy math, guys. If you're doing percentage and you've got a 100-gram sample, you got 52%, that means it's 52 grams. Then you calculate the amount of each element in the sample. So with diborane, the percentage composition, because the percentage was 78.1 and 21.9, your mass is 78.1 grams of boron and 21.9 grams of hydrogen. So now you move, the mass composition of each element is converted to a composition in moles by dividing the appropriate molar mass, which is calculations that we already know how to do. So you want to convert the grams of boron to moles. You set up your equation to get rid of the grams. You got 7.22 moles of boron. You do the same thing for hydrogen. Find you've got 21.7 moles of hydrogen. And these values give a mole ratio of 7.22 moles of boron to 21.7 moles of hydrogen. Then you find the smallest whole number ratio, and to do that you divide each number of moles by the smallest number in the existing ratio. So the smallest number in this ratio is 7.22. If you divide each one by 7.22, you get 1 mole of boron to 3.01 mole of hydrogen. We know that there's rounding, there's experimental error. You are always going to go with the nearest whole number for your actual ratio. So in that previous example, it would have been 1 to 3, which was what you got in your empirical formula for the diborane. It was BH3. What does this look like in a sample problem? You do quantitative analysis. You see that you have 32.38% sodium, 22.65% sulfur, 44.99% oxygen. You want to find the empirical formula. You've got your percentages. You go from percentage composition to mass composition, from mass composition to composition in moles, and then the smallest whole number mole ratio. That, guys, that's the track that you're going to follow. That track you're going to follow in doing these problems. So you, again, set up your problem here to get rid of grams, and you've got 1.408 moles of sodium. Get rid of grams, you've got 0.7063 mole of sulfur. Get rid of grams, you got 2.812 mole of oxygen. You see, you want to get the smallest whole number. Your ratio right now is 1.408 moles of sodium to 0.7063 moles of sulfur to 2.812 moles of oxygen. Divide by the smallest one, which is the 0.7063, and you end up with 1.993 moles of sodium to 1 mole of sulfur to 3.981 moles of oxygen. You're going to round those to the nearest whole number. So you get 2 moles of sodium to 1 mole of sulfur to 4 moles of oxygen. Your empirical formula is Na2SO4. Remember, that's your empirical formula. That shows you the smallest whole number ratio of moles. Does not necessarily show you the exact number of atoms bonded together. That would be the molecular formula. So then you got to move to molecular formulas. The empirical formula contains the smallest possible. We talked about that molecular formula is the actual formula of a molecular compound. And an empirical formula may or may not be correct molecular formula. So the relationship between a compound's empirical formula and its molecular formula can be written in this method. X, that's your unknown, times the empirical formula equals the molecular formula. So what that means is that you can work the calculation. The formula masses have similar relationship. Right? So X times the empirical formula mass equals the molecular formula mass. So to determine the molecular formula of a compound, you've got to know the compound's formula mass. You divide the experimental formula mass by the empirical formula mass, and it gives you X. A compound's molecular formula mass is numerically equal to its molar mass, so a compound's molecular formula can also be found given the compound's empirical formula and its molar mass. This chart shows you some examples, one where the empirical formula and the molecular formula are the same, a couple where they are different, and what N would equal in order to calculate that. But it's best to see it in a sample problem, okay? You've got a compound of phosphorus, and oxygen was found to be P2O5. That's the empirical formula. Experimentation shows that the molar mass is 283.89 grams per mole. So notice you're given the molar mass. What is the compound's molecular formula? We work this kind of using the same tools that we already have. You know this equation, X times the empirical formula equals the molecular formula. So X equals molecular formula mass over empirical formula mass. You know that the molecular formula mass is numerically equal to molar mass. So the molecular molar mass is 283.89 grams per mole. The molecular formula mass is 283.89 AMU. The empirical formula mass is the mass of phosphorus, mass of oxygen. The empirical formula mass, as you do the math there, is 2 times 30.97 plus 5 times 16 equals 141.94 AMU. You divide the experimental formula mass by the empirical formula mass to get X. In this case, 283.89 AMU divided by 141.94 AMU gives you 2.0001. That's X, so that goes in front of the empirical formula 2 times. You multiply the 2 through, which means you're multiplying it into the subscripts, and you get P4O10. And that is how you go through the process of determining the molecular formula. In this case, P4O10 is the molecular formula.